Join us as we uncover the Great Oxygenation event, when photosynthetic organisms released oxygen into Earth's atmosphere for the first time. This shift caused dramatic changes, leading to the decline of anaerobic life and the foundation for more complex organisms to evolve. Oxygen-producing microorganisms begin reshaping Earth's atmosphere, driving a dramatic transformation. While anaerobic life struggles to survive, this change fuels the rise of new, more complex organisms. Let's explore how this atmospheric shift set the stage for evolution. In shallow, ancient seas, dense clusters of cyanobacteria float near the surface. These microbial mats cling to rocky substrates, thriving under the sun. The water is rich with iron, capturing oxygen from the cyanobacteria, forming layers of banded iron formations. Expanding cyanobacteria mats blanket the ocean bed, bathed in soft sunlight filtering through the water. Iron-rich sediments settle in thin layers, marking slow but steady changes in ocean chemistry. Though the sky looks the same, Earth's future is being rewritten below. The ocean surface glistens under direct sunlight, where cyanobacteria bloom in vast numbers. Iron particles in the water create a shimmering effect. Over time, oxygen levels increase, hinting at future atmospheric changes as these simple organisms reshape the planet. Beneath a thick, hazy atmosphere, the ocean is filled with dissolved iron. As oxygen production begins, iron particles oxidize, creating striking red bands that sink to the ocean floor. These layers document the start of Earth's most significant atmospheric shift. Vast iron formations take shape, forming distinct bands of dark and light minerals. These layers reflect fluctuations in oxygen levels, preserving a record of early atmospheric changes. The still ocean surface reflects this transformation, signaling a major geological shift. The ocean floor is blanketed with vast iron-rich deposits, a testament to Earth's changing atmosphere. These formations extend across the seabed, preserving a record of rising oxygen levels. Their presence marks the lasting geological impact of the Great Oxygenation event. In a vast prehistoric ocean, iron particles are oxidized, turning the waters a rusty hue. The atmosphere above begins to gather excess oxygen, marking a pivotal shift. This environment teems with ancient life forms struggling to adapt to the changing chemical balance. Along the rocky shoreline, iron-rich stones are exposed to rising oxygen levels, forming striking red-banded iron deposits. Nearby, green microbial mats spread across the rocks, showing how life is adapting to this changing environment, shaped by Earth's evolving atmosphere. Across the vast terrain, early terrestrial life emerges, with microbial mats and simple vegetation spreading in oxygen-rich pockets. The sky, now clearer and deeper in colour, reflects the growing presence of oxygen, marking a major step in Earth's transformation. Anaerobic microbes struggle as oxygen levels rise sharply in Earth's primordial oceans, causing widespread microbial death. In this hostile environment, microorganisms are visibly stressed, with some decaying, illustrating the start of a mass extinction event. The devastating effects of oxygenation unfold as vast stretches of microbial mats wither away. Only small pockets of life remain in oxygen-poor refuges, highlighting the struggle for survival. This scene captures the harsh selective pressure shaping microbial evolution. As oxygen-tolerant organisms emerge, their vivid colours stand out against the fading remnants of anaerobic life. These small but resilient species signal a shift in Earth's ecosystems, marking the beginning of a new biological era shaped by rising oxygen levels. vast ice sheets cover the Earth's surface, reflecting sunlight with their bright white expanses. Beneath the ice, ocean water struggles to retain warmth. The atmosphere is filled with a thin mist, capturing the cold air, while the sun casts a pale, weak light. Under a frozen sea, life persists in the shadows. Cyanobacteria colonies spread across submerged stones, producing tiny streams of oxygen. Faint light penetrates the ice above, casting a deep blue glow on the underwater terrain, sustaining this delicate ecosystem. A barren, icy landscape with jagged glacial formations. The wind sweeps across the surface, leaving trails in the snow. Sparse, primitive life forms struggle to survive in the harsh conditions. The sky is clear, allowing the sun to cast sharp shadows on the ice. In a primordial ocean, single-celled aerobic microbes float, surrounded by swirling currents. These microbes, spherical and translucent, show internal structures adapting to oxygen-rich waters, marking a shift from anaerobic origins to oxygen-utilizing life forms. Along the rocky shore, primitive algae spread across damp surfaces, harnessing sunlight for photosynthesis. These early life forms thrive in shallow puddles where reflections of the sky shimmer on uneven terrain, signaling the first steps toward plant life on land. The seabed hosts diverse microbial mats, their layered formations adapting to the oxygenated waters. Gentle waves above shift light and shadow across the sand, creating a dynamic underwater scene that reflects the early evolution of life in changing conditions. Thank you for watching. Creating high-quality content takes a lot of time and effort, from research to production. If you enjoyed this episode, please like the video and subscribe to support the channel. Your engagement helps us continue making great content. Stay curious and see you in the next episode.